Thank you for the kind invitation. It's very nice to see everybody, and I see a lot of familiar faces here, so thank you so much for coming. So today's tutorial, it's going to focus on previous studies and previous work that has been recently done to explore fairness and sociodemographic bias in machine learning. And it's a compilation of material from both from papers as well as from some studies that have been done in industry. So let's start. So I would start by motivating this with a video that I found from Google. And in this video, they were asking people to close their eyes and imagine a shoe. So how would you think a shoe would look like? Many people would think that a shoe would look like that. Other people would think that it would look like that. Or other people would think that instead of this, it might actually look like that. So you can see here that there are a lot of different ways in which different people might perceive what a shoe looks like. Similar, if I tell you, how about a physicist? What would a physicist look like? Some people would think that a physicist would look like that, but there have been other physicists who would look like that. So there's a lot of discussion and a lot of thinking that has been going on recently on what are the inputs of machine learning algorithms, what are the data that we have been using to train our machine learning algorithms that have been used for our various tasks, and whether the data or whether the algorithms that we are using are biased towards certain beliefs and towards certain views of the world from certain people, and how inclusive are these algorithms with respect to society in general. So basically what this says is that so as we know, a machine learning algorithm basically learns whatever it sees. If we add pictures of the same shoe in the machine learning algorithm, or pictures of a shoe that always looks like that, then the output that it's going to recognize, it's always going to be a shoe that looks like that. Now, if we add additional data and additional types of algorithms in this, in our additional types of shoes in our algorithm, then we might be able to say and to instruct to our algorithm that a shoe looks both like that as well as like that. And in this way, the algorithm will be able to detect different types of shoes. The same thing if we have an algorithm that, let's say, detects previous physicists. If we only add, let's say, male physicists as an input to the algorithm, then the algorithm would only detect that this specific type of male faces is associated with the occupation of a physicist. So over these last years, there has been a lot of study and a lot of discussion, both in research as in industry, about how biased are machine learning algorithms towards what groups these algorithms are biased, and what we can do in order to design more inclusive algorithms. So this has been a recent study from MIT and NYU. So in this study, this PhD student had examined 4 different leading facial recognition platforms, and these facial recognition platforms were just basically to detect faces, as well as to detect different properties of the face, such as gender, age, and other properties like that. So this study showed that 2 out of 4 leading facial recognition platforms do not reliably detect African American users. So this is an example of how this algorithm can detect white American users. So this is the output of the algorithm here. You can see that the algorithm can reliably detect age, gender, for this specific input, for this specific facial input. However, when another facial input serves as an input to the algorithm, in this case of this African American woman, then the algorithm actually cannot find a face, in that picture. And let me say here that among the leading facial recognition algorithms that have been used in this study, these were actually from quite big companies. So there has been also another study, actually from the last year, about how voice recognition algorithms cannot reliably detect certain populations. So in this study, researchers compared 5 leading speech recognition programs, and they saw that some of them are twice as likely to make a mistake when they recognize the voice and when they recognize the speech content from African American speakers compared to white American speakers. So there has been a lot of discussion about how essentially socio-demographic characteristics can be included both in terms of visual information in images as well as in terms of acoustic information in speech signals. You can imagine that in speech there is not only the accent that is reflected, but also a different subtle intonation expressions that are inherent in speech and might capture socio-demographic biases without actually the algorithm explicitly modeling for such socio-demographic differences. And there is a big risk there. So beyond the gender bias and racial bias, you can also imagine if you have algorithms that are trying to capture different types of things. So in this case, in this example, if you have algorithms, let's say, that are trying to capture the degree of damage in a building, and you have buildings that correspond to areas with lower socioeconomic status and buildings that correspond to areas with higher socioeconomic status. You can see here the striking difference that we all know, that the appearance of different buildings depending on the socioeconomic status of the residents. And imagine if this difference now, it's not explicitly modeled in an algorithm, rather than the algorithm implicitly takes as an input different images in order to detect high-stake outputs. A high-stake output could be the degree of damage in a building after the disaster, after an earthquake, after a flooding. So there might be disparities going on there, just and solely depending on the difference in the appearance, rather than disparities that are related to the actual output that we might want to model. So having said this, in today's tutorial, we are going to discuss, first of all, what might be potential sources of a socio-demographic bias in machine learning algorithms. We are going to provide 2 examples, and those examples are mostly inspired by health, by physical health and mental health, about potential ways that we can capture and study socio-demographic bias in machine learning algorithms that are used to detect health-related outcomes. And in the second part of the tutorial, we are going to discuss some approaches that have been used in order to mitigate socio-demographic bias in machine learning. So this is the outline of today's talk. I wanted to mention here that please feel free to interrupt at any point with questions or discussion items, and I'm happy to provide more discussions related to this. So let's start. Let's start with a few ideas and a few position papers related to sources of socio-demographic bias in machine learning. So there are several types of bias that can occur in machine learning, and this can range from the input of the machine learning systems to the actual inner mechanisms of the machine learning model, as well as the way in which the machine learning model interacts with humans. So for the purposes of decision making. So if we were to now start with sources of bias that might be related to the input, meaning the data that is being fed into a machine learning model, we can have several examples of how this bias can occur. And the most obvious way in which this bias can occur is what we call minority bias. So essentially not having sufficient number of samples as we train our algorithm for a certain sociodemographic group. And of course, we are very much interested here in traditionally minoritized groups for which we might not have enough data. So for examples, we might not have enough data, let's say, from electronic health records for Hispanic Americans or for African American groups. And when we don't have enough data, the problem there is that our algorithm cannot sufficiently learn the representations that might be related to an outcome of interest. So let's say that we would like to compute and estimate the health risk of a person given or based on electronic health records. If we do not have electronic health records, enough number of electronic health records for a specific sociodemographic group, then this would mean that we cannot reliably represent the distribution of this specific sociodemographic group. And in this way, we might not be able to get accurate decisions for that specific group. There is also another discussion on how even bias can occur from missing data in a non-random fashion. So for example, when we have people complete self-reports, there is this amount of recall bias or even missing data bias that might not always be random, but might be systematic. So if you think about it, there might be certain types of people, certain types of groups that systematically have missing data. If you think about it, if we have people, maybe when people complete self-reports when they visit a hospital, there might be people with lower education levels or with lower sociodemographic status that might not accurately or sufficiently complete these self-reports. In the same way, if we have, let's say, for example, people completing electronic momentary assessments, which are self-reports that are completed via smartphone devices through an application. Usually what happens is that people who have a good smartphone device might have a seamless integration of that specific application on their smartphone, while people who might not have a good smartphone device might have, let's say, a slower smartphone device with a slower processor. Then in this case, completing the self-report might take a longer time. So this would really conflict with user experience, and maybe at some point, some of the people who might not have, let's say, a stronger smartphone device would give up in completing their ecological momentary assessments. And this might be a way in which bias might come from a non-random fashion from missing data. And finally, another type of bias in the training data can actually yield from the fact that there might be a lot of confounding factors that influence both input and output variables. So in this specific case, let's say that we would like to model a heart disease risk at an early age based on, let's say, a resting heart rate input. We know that gender can be a confounding factor for both the resting heart rate, just because there are gender differences in resting heart rate, as well as it might be a confounding factor at our output, because we know that there are gender differences in terms of heart disease at an early age. Now, if you think about it, a resting heart rate, it's only one physiological signal. Now, if this expands to signals that might be more inherently associated with sociodemographic groups, that might even be more dangerous. If you think about it, as we discussed, speech, which is a valuable biomarker for many behavioral outcomes, is really inherently confounded by the gender, We know that women have a higher pitch than men, as well as by racial factors. So the speaking style differs between sociodemographic groups, and also it affects the speech intonation that is being captured from the audio signal. Now, if this audio signal is being used, let's say, to detect depression or to detect anxiety or suicidal risk, then we can see how the confounding factor of race or gender plays is integrated both into the input, which is the intonation or the spectral characteristics of the speech, as well as the behavioral output. So a second source of bias might actually come also from the actual design of the model. And in the actual design of the model, we might have bias that might come, let's say, that might yield from the fact that if we apply the same threshold when we take our decision from the model for all individuals, this threshold might be good for some individuals, but it might not be good for other individuals. Another potential way in which bias might be integrated into machine learning models is if we do not adequately represent the different subgroups in our data. There is definitely a lot of discussion about how different racial groups can be represented in the data, how different non-traditional groups can be represented in the data, for example, protected groups such as LGBTQ, and other groups. We know that usually many studies, now this has changed, but traditionally many studies have been considering, let's say, a binary representation of biologicals of gender, represented as biological sex, as only male and female, without considering really other representations and different levels of granularity. So we can see that if the machine learning algorithm only has this binary representation as an input and doesn't have any other representation, how this might lead into decisions that are not really accurate and precise for different groups. Finally, a big issue when we are trying to examine bias is yields from the fact that many times algorithms that are being used on a wide scale are proprietary algorithms. So, for example, computer vision algorithms from Microsoft, from Amazon, from Google, all these algorithms are proprietary. We have no access to the inner mechanisms that are being used both to train as well as to make the decision. And for this reason, it's very difficult to understand what are specific mechanisms and what are specific sources of bias that might be integrated into these proprietary algorithms. For many of these algorithms, we might not even have access to the raw data that have been used to train them. So the only way to actually understand this is basically if we probe them with certain inputs, and then we try to see what comes at the output. And this is one way, obviously, but we do not get the full picture of actually having both the data that have been used to train those algorithms, as well as any inner mechanisms that have been used in order to learn these data representations. There's this question here, let me see. So there is a question here from Dr. Ramasubramanian, whether there is any pressure on big tech to share the algorithms. So I have to say here that there has been a push from big tech in order to share some of these algorithms. So, for example, algorithms such as neural networks that rely on object recognition like VGZ16, VGZ19. Some of these networks have actually been shared by the big tech, as well as with the corresponding data that are being used to train those algorithms. But obviously that's not enough, right? Because we know that there are proprietary algorithms there for facial recognition. And I think that the big problem there is that these proprietary algorithms are also being used for commercial purposes from companies. And that's how it might be actually very hard to share at least the full-blown algorithm. And I think there is definitely a progress over the last years on actually sharing at least part of some of these algorithms. But definitely we have a long way to go. Give me one moment here. I cannot see my cursor here, so I cannot really understand.
Thank you, Theodora.
Of course.
Yeah.
Okay. So a third type of bias that might come that might be integrated in machine learning algorithm is now at the output level, when the decision from the machine learning algorithm interacts with experts. Especially for high-stake conditions, such as health conditions, we know that even at this point, it might not be 100% feasible to basically have only a solely automated system to take the decision, the responsibility of the actual decision making. And at least for the near future, we expect that the decision of the system would be somehow integrated with the decision of the expert, maybe a stakeholder or a clinician, in order to result in the final clinical decision. So that by itself can be a tricky process. And the reason for this is that us, as humans, have obviously our inherent biases. And of course, clinicians and health experts are trained in order to mitigate those biases and to be aware of their inner biases, but they are still humans. And if this human decision-making process now is being combined with an algorithm that is potentially biased, then we can understand that bias and unfairness might actually propagate in the final decision-making process. So what might be different ways in which this propagation of bias might happen? First of all, we can have what we call automation bias. And automation bias yields when experts are unaware that a model is underperforming for a certain group. And that means that usually an expert tends to blindly trust the decision of the machine. There has been an extensive literature on automation, not much in terms of machine learning, but in terms of automated systems that have been existing for the last decades, and on how experts who do not have much experience either in the field or when interacting with the automation system can blindly trust the system. So we expect that some of these might propagate in machine learning systems, where essentially, let's say in cases where we have a young physician that doesn't have much clinical experience, let's say in the emergency room, and the machine learning system, let's say that we have a machine learning system that prioritizes patients based on a decision from the algorithm. So in this case, if this system is biased and interacts with a less experienced physician, then there might be actually decisions that might be highly risky for certain groups. There is one more question here. Thank you very much for the question, Aniruddha. I will definitely get back to you because we have a lot of thoughts about inherent human differences, and I'll get back to it after we're done in a few slides. So basically, if I may continue a little bit here, there has been definitely studies which have showed that even for the most, even for mental health experts or for people who have been doing, who have been practicing their profession for a long time, if there is no systematic awareness and there are no systematic reminders on inherent biases, how these biases can propagate. So, for example, there have been studies from ER Room which indicate that white physicians are less likely to administer painkillers and administer some type of therapy for African Americans compared to African American physicians. And the reason might be either that there might be misconceptions or other sources of bias that might come there. So we can understand now when, again, when we have this biased decision making that interacts with a biased machine learning algorithm, how these things can propagate. And on the other time, beyond the automation bias, which is the blind trust to the system, we can also have what we call dismissal bias. So let's say that we have a system that constantly triggers false alarms. Let's say that maybe now we have a system that is oversensitive for a certain sensitive population, and this system actually continuously administers false alarms. So in this case, we might have a dismissal bias just from the fact that a clinician or our human stakeholder might be desensitized from all these false alarms. And finally, the final source of bias in machine learning can be in terms of the interaction with the user. So we can have what we call privilege bias, where the machine learning model might be unavailable in places where specific groups receive care. So for example, if we have devices with low computational resources, here you can see a smartphone versus a very cheap, like an iPhone versus a very cheap smartphone, there might be actual issues in terms of how the user interacts with the system and in terms of how available even the system might be to the user. And of course, we have traditional groups that due to historical exploitation practices, we have traditional users who might be very skeptical and biased against any type of automation or any type of service like that. So I think this might be a good time to come back to two questions that are in the chat. So there is a question from Dr. Ramasubramanian about dismissal bias and whether not all are false alarms. Yes. So basically, the dismissal bias refers to the fact that sometimes it might be very difficult to have a system that like usually I guess as researchers, we are more prone to have a system which has a higher number of false alarms rather than missing risky events, right? So if a clinician, so let's say that there are 5 false alarms and 1 or 2 true positives, right? So if the clinician is very much used to seeing this high number of false alarms, then he or she might think that the single true positive that he or she sees is also a false alarm, which might not be the case.
Okay, yeah, thank you.
So let me go back to the other question about machine learning algorithms being more inclusive to basically any type of human differences. So I think that is a very good point. In many communities, so in psychology, for example, in psychological sciences, traditionally there has been a lot of work about individual differences and how different types of people might depict different representations, different signal representations, different biomarkers with respect to a single outcome. An example here, let's say, is resting heart rate, for which we might have gender differences. That's why the thresholds, the risk thresholds for men and women or for different ages might be different. recently in computer sciences and in affective computing in specific, there has been a lot of work about how to integrate individual differences. And our group, along with many other groups, have been done a lot amount of work on how to build personalized models, group-specific models, where it's not only sociodemographic clustering that occurs, but clustering with respect to other characteristics. So it might be clustering with respect to psychological characteristics, let's say personality characteristics, trait anxiety characteristics, or any other types of characteristics that makes sense for the outcome of interest. And if you're interested in that, I'm happy to also discuss with you after the talk. So that brings us to the next part of our talk, in which I selected two different studies to showcase how sociodemographic bias can occur within machine learning algorithms. The first is a published study from 2020 that looks at how electronic health records can be used to predict risk and how there might be an inherent disparity when doing that. The second study is a preliminary pilot study from our lab in which we used a set of multimodal data to predict family well-being. And in this case, it was multimodal data from couples. And we tried to predict when conflict is going to occur between couples based on a set of multimodal data. This is a very small pilot study that we have done on how on how we might have disparities across sociodemographic groups during that decision-making process. So let me start with the first study about the electronic health records. So this is a study that was published in Science in 2019. And in this study, basically, they used a commercial risk prediction algorithm, which was applied to 200 million people in the US. And this algorithm apparently is applied across many settings and is being used in order to, of course, improve patient care, because the whole purpose is that we are trying to predict which people are at the highest risk, and we are trying to intervene early for this specific set of people in order to make sure that they receive proper care and in order to make sure that there might be no chronic conditions that occur in the next 5 to 10 years. So these algorithms are also used to identify which groups and which people are going to receive greater attention from their physicians, and also towards ensuring a more well-coordinated care. So the data here comes from primary care patients enrolled between 2013 and 2015. It includes around 6,000 instances of Black and African American patients and 43,000 instances of white American patients. 70% of those patients were enrolled in commercial insurances and 28% were enrolled in Medicare. And the average age of these patients was approximately 50 years old, and 63% of these patients were female patients. So the way the algorithm used, and again, this algorithm was a proprietary algorithm, so we have no knowledge about the inner mechanism, like this brain here, that actually goes into finding associations between the input and the output, but we know what the input and the output is. The authors know what the input and the output is. So the input in this algorithm were the demographic characteristics, excluding race. So basically biological sex, age, and other demographic characteristics. And another input was the insurance type, IDC-9 codes, which are essentially correspond to a classification of a disease, prescribed meditations that might be registered as part of patients' electronic health records, several exams and medical service encounters, such as when people had an appointment with a doctor, what was the type of the appointment, treatment, what were the exams that were being made, as well as billed amounts to the insurance. So basically, all the cost to the insurance that has been that had been applied as part of the patient's care. So these were the features that were used as an input to the algorithm, and those were the features that were registered, let's say, at year 1. So the algorithm was trained in order to predict the total medical expenses at year 2. And based on these total medical expenses, the algorithm basically, after that, the 3%, the 97th percentile of the patients who depicted the highest medical expenses were the ones that the algorithm basically notified those patients in order to receive a more intensive care as part of some type of intervention. Between the 55th percentile and 97th percentile, the algorithm sent those patients to a physician, referred those patients to a physician in order for the physician to discuss and to make sure that these patients receive care. And the patients for which the algorithm depicted a risk lower than 55%, these patients basically were not part of any additional intervention. So basically what the authors of this paper did is that they compared the percentile risk of the algorithm that the algorithm learned against the number of active conditions of the patients. So the percentile algorithm risk score is essentially the output, as you see here in the x-axis, is the output that the algorithm provided when considering as an input all the patient's characteristics, so age, gender, insurance type, and all the other patient's characteristics. Now, the y-axis here is the number of active chronic conditions, including cardiac diseases, diabetes, and all other chronic conditions that each patient depicted for every risk score. And you can see here, the authors plotted basically these two variables for two different groups of patients. In this case, white American patients and African American patients with the yellow and the purple line. And this difference, of course, was made because of historical differences between those two groups. So what we can see here is that for the same level of risk prediction that is being detected by the algorithm, we see that the group that belongs to African American patients has a substantially higher number of chronic conditions. And the authors also itemized this risk in relation to the chronic condition. So in these four figures, you see different biomarkers that might be related to heart disease, diabetes severity, hypertension, and other things. So you can see here in the upper left figure that for the same algorithmic risk score, African American patients had a higher fraction of uncontrolled blood pressure compared to white American patients. The same thing happened with HbA1c. HbA1c is a blood biomarker for diabetes severity, as well as with several other measures. So what does this say? This says that if, let's say, an algorithm predicted 97% score for a certain population, this 97% score essentially corresponded to different disease severity for the two subgroups of people. So for the same algorithmic score, essentially, African American patients depicted a higher disease severity compared to white American patients. So after that, what the authors of the paper did is that they tried to see what was the reason for which this might have happened. So what they also compared medical expenditures across patients, which we see that there might be pretty similar. So another thing that they did is that basically they tried to compare the mean total medical expenses for the same chronic conditions between white American patients and Black American and African American patients. So we can see here for the same degree of chronic illness condition, the average total medical expenditure for white American patients in this specific data was found to be higher, slightly higher, compared to the average medical expenditure for the African American patients. So what this alludes to, it might allude to the fact that since the algorithm was actually trained to predict the total cost of medical expenditures over the next year, basically, the algorithm is being trained to predict which are the people, who are these people who are going to cost more money. And because white American patients basically had a higher medical expenditure, and the reason for this is that maybe there is higher awareness, people might go more regularly for an exam, more regularly to the doctor. That's why medical expenditures might be higher. That's why basically these algorithms were trained, and they identified that who are these people for which these medical costs are going to be higher. And that's why basically they might have identified more white American patients for the same degree of risk compared to African American patients. So after doing that, what the authors did in this study is that they tried to replicate the same algorithm, but they now trained this algorithm with 3 different outputs. So output 1, again, is the total medical costs for the next year. Output 2 is the avoidable medical costs. And output 3 is the active chronic conditions. And what you can see here in these bar charts, which represents the percentage of African American patients now that belong to the group with the highest predicted risk, which is the 97th percentile, you can see here that while when the algorithm was trained with having as an output the total medical costs, it only predicted that 14% of the African American patients are at the highest risk. When the algorithm used as an output the active chronic conditions, then instead of the 14% of African American patients, it predicted 26% of these African American patients that might be at increased risk. So essentially, what we understand from this study is that input and output matters. There has to be a high awareness, and there has to be basically a lot of exploration of what goes in and what comes out in the machine learning model. And depending on that, we can actually really influence decision-making policies and actually influence human lives. So the last study that basically we're going to discuss here in terms of how sociodemographic bias can be examined in machine learning is a study about couples. And in this study, our group had tried to detect interpersonal conflict between couples based on ambulatory data. So in this study, we aimed young couples just because we know that basically whatever people do at an earlier stage of their lives might also affect them moving forward. And we wanted to see how young couples behave not only inside the laboratory in very constrained conditions, but also outside the laboratory in the real lives using wearable and ambulatory-based devices. So for this reason, we had used a smartphone device, which was employed to collect self-reports as well as speech signals and language measures. And we also used 2 wearable devices that collected electrodermal activity signals which is essentially the amount of sweat that is being elicited from the human body, as well as another device that was used to capture two lead ECG signals, which measures heart activity. Now, you can see here how different discrepancies, how there might be differences with respect to the input data and potentially with respect to the output data across socio-demographic groups. Basically, in the example that we discussed about voice activity recognition and about how different factors might actually influence acoustic measures or linguistic measures, this might be highly relevant here. So we wanted to see essentially if we train a simple machine learning algorithm using these multimodal features as an input, and as an output using a binary label of conflict versus non-conflict, whether the decisions of this algorithm might depict differences across socio-demographic groups. And because these were basically couples, and in this case heterosexual couples, so we had the same number of male and female participants, we only basically made that comparison in terms of racial disparities and in terms of age disparities. So in this algorithm, we used a 5-fold cross-validation, stratified cross-validation to train. By stratified cross-validation, I mean that no sample from the same couple was used both in training and testing. So in this way, the algorithm was couple and subject independent. And we used 50 couples, which in total yielded approximately 1,400 samples, from which approximately 500 represented conflict and the rest represented no conflict. Here you can see the participants' demographic distribution. We see that almost 1/3 of these participants were white Caucasian participants. Another 1/3 was Hispanic Latino. The data were collected from Los Angeles metropolitan area, which reflects this diversity of the area that there is there, of the population that there is there. We also had 10 Asian American participants and 11 Black African American participants. In terms of demographic distribution, almost half of the people were between 18 and 22 years old, and the other half were between 23 and 26 years old. It's mostly the typical distribution of undergraduate versus graduate level students. So we wanted to see, first of all, whether there are differences among groups with respect to the adherence to answering self-reports. So what happened was that participants had to answer electronic momentary assessments every hour. And we wanted to see whether, first of all, how many reports were completed, how many reports were missed, and then whether there is a certain difference across groups. So we see here that, let's say, among Asian American participants, 61 times participants completed the self-reports versus 88 times that missed the self-reports. Similarly, for African American participants, we see 103 times people completed versus 56 times that people missed self-reports. So I think you can understand what was going on there. So we can see maybe several differences with respect to adherence to self-reports. Now, similarly with age, we didn't find any significant differences. So between, let's say, undergraduate students and graduate students, we saw pretty much the same percentage of the number of people of the number of missing versus the number of completed self-reports. And after that, we wanted to see whether there are discrepancies between the self-reported and the algorithm detected conflict with respect to age. So in the first part of these plots, you can see essentially how many times conflict and non-conflict was reported with respect to our 4 different groups. So you can see here that for Asian American participants, 4 times conflict was reported versus 57 times that no conflict was reported. For the African American participants, 16 times conflict was reported versus 87 times that conflict was not reported. Then for the Caucasian participants, 22 times, 22 conflict instances versus 200 conflict instances, and so forth and so on. So then you can see the results of the algorithm in the second part of these charts. So you can see, let's say here, that for African American participants, the algorithm detected 55 instances of conflict versus 48 instances of non-conflict. For the Caucasian participants, the algorithm detected 2 instances of conflict versus 237 instances of non-conflict. And at the last graph, at the last part of the graphs, you can see the average unweighted accuracies for each demographic group. So you can see essentially how well the algorithm detected conflict for each demographic group. So we can see here that, let's say, for Asian American participants and Hispanic Latino participants, the algorithm performed the best, while for African American participants and Caucasians, the algorithm performed the least performed the worst. A potential reason for that might be the very high mismatch and in terms of percentages of conflict that was reported between the 2 groups. So we see here that in terms of the 100 instances of conflict of self-reports that we have from African American participants, 16 out of these 100 were reported to be conflict instances. And that was a pretty significant percentage. So essentially 16% of instances were reported to be conflict. Whereas for Caucasian participants, it was pretty much 1/2 of this. So 22 out of 240 instances were reported to be conflict. So we suspect that this might be a potential characteristic that this algorithm might have picked on. So essentially, when the algorithm might see speech characteristics that belong to African American participants, then automatically the algorithm might say that this is a conflict instance just because a high percentage of instances that belong to African American participants has conflict compared to a lowest percentage of instances for the Caucasian participants. This is just a speculation at this point. This has been some study that we did in our lab in the past 4 or 5 months. We really would like to examine what's going on beyond that, whether there are significant sociodemographic instances, which we expect that there should be with respect to our input features, with respect to our speech signals, and whether there might be further differences with respect to the whole spectrum of the AUC curve. But these are just some preliminary results that might actually describe some sociodemographic disparities that might occur both in terms of self-reporting, in terms of data, as well as in terms of decision-making of the machine learning algorithms. Similar results were run for the different age groups, but there hasn't been really much discrepancy and much difference and a large amount of differences between age groups. So there is a question here, and I think this is a very good place to ask a question, because after that we can take a break and we can go to the second part of our talk. Thank you. So part 2, we are going to discuss a little bit about how prior work has started thinking about how to basically mitigate similar sources of sociodemographic bias when learning and when training machine learning models. And at the end, we're going to provide a few guidelines on how engineers can work hand in hand with social scientists in order to alleviate this problem. So in terms of machine learning approaches, I'm going to discuss 3 machine learning approaches, including adversarial learning, fairness, regularization, and explainability. These by no means are the only approaches that have been proposed. This is what I found to be a little bit most relevant for human-related data. So let's start with adversarial learning. There has been a lot of work in computer vision and in machine learning about how we can eliminate one's identity and how we can use adversarial learning approaches to do that, and essentially how this can actually lead to more fair machine learning algorithms. And you can understand that when we eliminate someone's identity, then at the same time we can eliminate their race, their gender, their age, and this actually can reduce the amount of sensitive information, but at the other hand can actually preserve some amount of information that is relevant to a primary task of interest. Let's say if we want to predict depression risk, we might be able to eliminate sociodemographic information from the speech signal, which is the secondary type of information, but at the same time preserve clinical information related to depression. So this is a study that we did in our lab over the past 1.5 years. The goal of the study is to train anonymized image-based models for emotion recognition. And we followed this adversarial learning approach that has been also widely used in computer vision and in machine learning for the more general stuff of human activity recognition. So there are some subtle differences between the task of emotion recognition and general human activity recognition. The first being that usually for general human activity recognition, the vision frame, the frame of the image is being captured from people's whole body, or at least upper part of the body. This means that the pixel information that we have that's relevant to the face, which is the most relevant part of the image that preserves the person's specific characteristic, is not as detailed in the human activity recognition problem, just because we have more information that is being related to the whole body. In contrast, when we have an emotion recognition problem, usually we are very much interested into that facial expression here, as we can see. So we most of the times we have images that only have this facial expression. And also, of course, basically some of the pixels that might be related to emotional expression are also related to a user identity. So we wanted to see how we can use an adversarial learning approach in order to suppress information that is being related to the identity of the user, but also preserve information that's being related to emotional expression. So for this reason, we use 3 types of data sets. All of these data sets have facial expressions and the facial region in the entire region of the image. These data sets are publicly available. So the first and second, they are the Japanese female facial expression data set and the widely available Yale face data set. These are mostly more constrained data sets developed under very constrained environments, and also they reflect acted facial expressions, which means that people were instructed to depict that emotion, to depict a facial expression with a certain emotion. On the other side, the last data set, which is called IMOCAP data set, not only is larger, but also it contains more spontaneous emotional expressions. Therefore, it is slightly more complicated compared to JAFE and Yale. So in the first research, in the first question that we tried to answer was whether we can characterize and quantify user identification risk based on from the emotion recognition models that we use our data to train. So to do that, we first trained the convolutional neural network only for the task of emotion classification. So the input of the convolutional neural network was the image, the facial-based image. The output was the emotion ID, and then the inner layers of the network were trained so that they can learn representations, visual representations that are related to the emotional information. Now, what happens there is that we wanted to see how much of the information that is inherent in these visual representations, how much of this information might be also related to facial information. In order to do that, we froze the convolutional layers, and then we fine-tuned the last fully connected layers of the convolutional network for the task of user identification. And then we wanted to see whether these convolutional layers, the inner convolutional layers that have been solely trained for the task of emotion recognition, how much speaker-independent information they have preserved. And we see actually that these models have preserved a substantial amount of user information. So you can see here that basically the first set of the bars presents just user classification, the percentage of user classification accuracies, where we have a convolutional neural network that is being trained solely for the task of user classification, and that serves as a baseline to understand what might be the upper bound of performance that we can get for user classification, and we can see that this is pretty high, as we have been expecting. Now, when we get this convolutional neural network, we train it for the task of emotion recognition, and then we freeze the convolutional layers, and we only fine-tune the last layers for face identification, then these are the results that you see in the right part of these graphs, in the last essentially three bar charts here. So you can see essentially that these emotion recognition models, if it is retrained for the task of user identification, then this actually yields pretty good user identification accuracies. And this occurs not only when we have the original unblurred image, but also when we blur our image, which means that when we train emotion recognition, when we train neural networks and machine learning models for a primary task, let's say the emotion recognition task that we have in mind, then these emotion recognition models might actually preserve a substantial amount of user-related information. And then in extension to that, they might also preserve certain sociodemographic biases that come from the fact that they have actually preserved the user ID. So then we wanted to see how much an adversarial learning approach that can be learned in order essentially to learn only emotion-dependent information and unlearn speaker-dependent information, user-dependent information, how much this approach can help. So in doing so, in our first effort, we tried to train this adversarial neural network just like that. So essentially, we had this loss function that was essentially, we wanted to reduce the emotion-related loss and increase the user-related loss. That was the first iteration that we tried. And as part of the second iteration, because we saw that the first iteration was really stuck many times in global max, in local minima, what we did was that first we trained we essentially froze the parts that were related to the emotion classification model. Then we tried to learn a user identification model, as you see here in the red, in the layers that are depicted with red color. So we tried essentially to learn a user identification model based on a good emotion identification model. And then after that, we tried to unlearn this good user identification model. And this is essentially a min-max problem. And we saw that when we actually perform this approach, we can get some better and more robust results. So here you can see in the first part of the graph of this plot the original images which had the facial the images of the face. In the second row you can see the transformations of the CNN that was trained solely for the task of emotion classification, and you can see that essentially in this second row of images a lot of facial information is being preserved. So a lot of information related to the structure of the face, the facial characteristics such as lips, nose, eyes, as well as the shape of the face. All this information is being preserved. In the last part, you can see the information that is being preserved from the anonymization algorithm, which has been trained with the proposed adversarial learning approach. So for this anonymization algorithm, you can see that only very specific parts of the image have been preserved, parts that are mostly related to the eyes and some parts that are being related to the mouth, but not specific parts related to the shape of the face. So here you can see the results that we get that we get from the proposed anonymization algorithm, which is with orange colors, in terms of both emotion recognition and user identification. So you can see essentially that the orange bar graph here still preserves a decent amount of emotion recognition accuracy, which is what we wanted, because we want to have a reliable machine learning model that performs visual-based emotion recognition. But at the same time, we would like to have a machine learning model that unlearns user-specific characteristics. So the orange line essentially is very much minimal in terms of the user identification accuracy, which is the result that we wanted to observe. We are now, and there have been other studies which have attempted similar approaches for the task of, emotion classification and gender recognition. So emotion classification as a primary task, gender recognition as a secondary task, which is the task that we wanted to eliminate, or emotion classification and race recognition. So this goes to say that by formulating these adversarial learning problems, mostly in terms of min-max optimization problems, we might be able to learn signal representations. Either these are visual representations, or these are acoustic representations, or linguistic representations that might be relevant to the actual task that we would like to learn, and might suppress information related to sociodemographic bias that we would like to unlearn. So in this case, we might be able to mitigate some of the disparities that come in the decision-making process. Still, there's a long way to go about how these adversarial learning approaches might work in terms of mitigating biases and in terms of actually yielding unbiased decisions from the data. Now, as part of the second approach that has been proposed to mitigate sociodemographic bias, this second approach is called fairness regularization. So what researchers have done there, and this is actually from another paper, it's not part of our work. So what researchers have done there is that they specifically defined a discrimination score, and they learned the algorithm such as the discrimination score is as low as possible. So the way the authors defined this discrimination score is that they looked at the difference between the distribution of the risk between the sensitive group and the non-sensitive group. Let's say the sensitive group might be Hispanic Latinos, and the non-sensitive group might be non-Hispanic, non-Latinos. And they wanted, so basically by looking at the difference between the two distributions, essentially what they wanted to do is that they wanted these two distributions to converge as much as possible. So in doing so, they actually introduced this discrimination score as an explicit term in the learning function. So the learning function contained, of course, the loss function of the algorithm. If the algorithm, let's say, is a feed-forward neural network, it's going to be the cross-entropy loss or the regression loss of the feed-forward neural network, and so forth and so on for any type of other optimization algorithm. Beyond that, they also introduced this discrimination score that they wanted to minimize, as well as they also imposed some regularization for the classifier in order not to overfit. So you can see here the results that yield from this work. So the first result is basically the result from an adversarial learning approach, which was used as a baseline for fairness regularization. The second is the result of a non-adversarial learning approach that basically maintains equality of votes similar to non-bias mitigation. And the last result that we see here is if no regularization or no debiasing is being performed. So we can see here that basically the adversarial learning approach in this case yields a lower discrimination bias compared to both the fairness regularization approach and no bias mitigation. However, we also see that this adversarial learning approach also has a very high variability in terms of the discrimination scores that it yields. And based on our experience and what we have actually seen with all these adversarial learning approaches, a potential reason might be that many of these adversarial learning approaches get stuck in local minima, and then it's very difficult to learn something better beyond that. The authors also, what they did is that they wanted to see how consistent is the regularization fairness approach compared to the adversarial learning. And they saw actually that the regularization fairness approach tends to be way more consistent. So so essentially the discrimination score between the sensitive and the non-sensitive group is consistently the same across all samples of the data in comparison to the adversarial learning approach, which sometimes might achieve good performance, but there might be other times where the performance of this adversarial learning approach might actually be pretty weak. So finally, I just wanted to mention here that another potential way in order to at least dissect some of these discrepancies and some of these biases that might occur in these machine learning algorithms, it's through understanding better the model. And we know that basically there is a spectrum of explainability, and there are of course a lot of people who are working on explainability both at Texas A&M and beyond Texas A&M, but definitely explainability is a great approach to do that. And the reason is that at least we are trying to understand what is the reason that led to the machine learning algorithm of taking that decision. So, of course, there is a spectrum of explainability. There are models who are simpler, and therefore they are definitely easier to understand. But there are models also who are more complicated, let's say, such as convolutional neural networks, which are more complex and more difficult to understand. So this is where explainability might come into play. What I wanted to say here is that there are multiple ways that have been proposed in order to yield inexplainable models. This is actually one of the things that we discussed in our machine learning class and in our special topics class this semester. And this is basically one of the most well-known explainability models, the local interpretable model agnostic explanations. The big advantage for this specific model, whose code is also publicly available on GitHub, is the fact that it is model agnostic. So essentially, you can have any algorithm, even if this is a black box algorithm, and you can provide input and output, and it can at least provide some type of explanation of how the decisions were being made. So by getting these explanations, we might be able to study those explanations and better understand what might be reasons that this decision was being made, and therefore we might be able to better understand what's going on in terms of sociodemographic biases and in terms of disparities among groups. This is an example where essentially through, I think the input here was just a patient's symptoms, and the output here was what type of medication to administer to the patient. And you can see here as an explanation what are essentially the most important features that were rated by the Lime algorithm as the ones that contributed most to the model. So you can see here essentially how this could be used in order to detect biases. Let's say if we have a feature explicitly like as a feature related to a sensitive group, or if there are features that might be inherently different across sensitive and non-sensitive groups. So how this could play into the actual decision making. Finally, what I wanted to also highlight here are some general recommendations for fair machine learning, and how engineers and social scientists and life sciences researchers could work hand in hand in order to achieve more fair machine learning. Before I go there, there is one question. Oh, sorry, there is no question. So let's jump into the guidelines, and if there are any questions about some of the machine learning methodologies, I'm really to answer either now or after the end of the session. So what might be some general recommendations in order to achieve more fair machine learning? I think the first and foremost might be to try, first of all, to define the goal of the model and review the model with diverse stakeholders. I think this goes back to the example of the shoe. Like if you only have, let's say, male colleagues who actually provide data that might be related to a shoe, this shoe might be only, let's say, in terms of a sneaker, or in terms of more like regular shoes that we have every day. Now, if you have also female engineers who can also provide examples of shoes, then these might be different types of shoes, such as sandals, high heels, and all these things. So basically, the main idea there is to have diverse stakeholders and diverse engineers review the models and review the design of the models, and make sure that at least at the design stage, this we have taken into account any potential discrepancies across groups. The other issue would be to also discuss ethical implications and ethical concerns about how the model might essentially overestimate or underestimate outcomes for sensitive and protective groups. And again, I think this goes to the part of hand-in-hand collaborations between engineers, social scientists, and health scientists in order to better understand what might be ethical risks and implications from the design of the machine learning algorithm. The second point there is in terms of data collection. So first of all, when we collect data, it's very important to collect and document the training data. And by documentation, we mean basically document from which participants' data came from, because this is the only way that we will be able to track the machine learning algorithm, and it will be the only way to understand whether our algorithm might be biased against people. And of course, there are all the security implications that come with this, which definitely are at the capacity of various groups and various researchers in order to be able to do that. An important issue there, of course, as we have said multiple days, is to make sure that the data from the protected group is adequately represented, both in terms of numbers as well as in terms of features. So basically, if we have, let's say, going back to the original example about binarized gender representations, make sure that basically we don't only capture biological sex, but we also capture gender. And that's, of course, not only male and female, but also other LGBTQ groups. In terms of other ways, it's also important to make sure that the quality of the data is similar across different groups. And if it's not similar, it's also important to take that into account. That goes back to the example of iPhones versus less expensive smartphone devices. So how different groups from different socioeconomic status might have just different quality of data because they have better resources into getting access to more effective and more reliable data capturing devices. Finally, there is definitely a lot of discussion in terms of training, evaluation, and deployment of the models. When we train and evaluate the models, I think at this point it's crucial to take into account fairness goals, make sure that we don't only evaluate in terms of performance, but we also evaluate in terms of discrepancy scores. Make sure that we examine differences in the algorithmic output between sensitive and non-sensitive groups. And also, after we are done as engineers, after we have done our part, make sure that we discuss with our non-engineering colleagues and our social scientist colleagues about the outputs of the algorithm and about whether there might be potential biases in terms of the output of the algorithm that we haven't thought. Finally, at the last stage of the deployment of the model, it's very important to, when we deploy the model, to systematically review the data and continue to evaluate the metrics. Again, metrics not only in terms of performance, but in terms of fairness. And the important reason for that is that when we deploy the model, essentially we get more data. The more data we have, the more opportunities we have to expand the evaluation of the model. And usually the more data we get, the more glitches we can find into our system. Not only glitches, the more weaknesses, the more substantial and significant weaknesses we can find into our system. So I think I will end with that. If there are any questions or any